having the little camera. And is it going to focus? No, yes, very slowly. Okay, I'm just going to have to believe that it's going to work. So, and we start this. So we're recording there, we're recording on the little camera. Everything is good. And so today we're going to be talking about easy, well, maybe easy stuff, not, okay, familiar stuff. So I think in previous courses in 2110, you've done breadth first and depth first traversals, right? So you know how to do a breadth first and depth. Did you do topological sorts and strongly connected components? Oh, you did topological. Oh, okay. So this should be easy. In that case, some of this is going to be a review. So today we're going to be doing, well, DFS, DFS, and Dijkstra's. And for the DFS, so the example of DFS is mainly going to be Dijkstra's, and DFS is going to be topological sort. And yes, I did start that. And strongly connected components. I'm not sure if strongly connected should have a hyphen. Yeah, probably it should be strongly connected, but I'm not sure about this. Okay, so you know what a depth first, so depth first traversal, depth first search of a graph, a breadth first traversal, breadth first search. And also, please remind me if I jump straight to Dijkstra's algorithm, I also want to talk about things like DFS comes up a lot in AI because you're doing state space exploration. So for example, if you want to do that thing where you have a cabbage and a goat and a wolf and you want to get them across, and you have these states and you can transition between some states and you explore the state space, the minimum number of steps, minimum number of times you need to go back and forth across the river in your boat is you find that by finding the shortest path between the state where everything is on the one side of the river and the state where everything is on the other side of the river, and you usually do that with BFS. The same thing. I'll probably put this on the assignment. The thing where you have jugs and they have a certain size, and you want to measure out an amount of water that's a different size. You do that with BFS. Okay, I'm not going to say. Okay, you need to know that in a DFS and a BF, so in particular, a DFS, you have your graph and you start at some vertex and you're doing an exploration, and it can be a directed graph. Right? So in a directed graph, you're only allowed to go across the edges in one direction. And whenever you visit, whenever you first arrive at a node, then that you have a clock, and every time you do something, the clock ticks. And when you arrive at a node, you say, okay, that's its discovery time or its start time or whatever. And then the last time you visit the node, you'll be like, yeah, okay, I'm never coming back here again. That is its finish time. Okay. So start time is when you first visit, and finish time is when you last visit. Okay. And that's important. So visited flag is a little, because you also in the book, in the CLRS, there's this thing about like, oh, you color the nodes before you visit them, they're white, and after you visit them, they're black. And when you're still in the process of, you haven't reached the finish, you're between the start time and the finish time, they're like gray or something like that. So that's just like you have a marker that says I've been here. But the start time is like when you first arrived, and the finish time is when you last arrived. And these are important in these two algorithms. So let's just do so because we're going to break this down into because just going to check it's recording. Doesn't seem to focus. So what was I going to say? I forgot what, it can't be important. Okay, so now, first we're going to start with topological sort. Now the example from the book, do we want to just copy it from the book, or should we do it ourselves? I think it's harder for me to, so it's somebody getting dressed in the morning, okay? And so you have things like shoes, shirts, underwear, okay, so to make this interesting, vest, hat, tie. I think they also have, what have I got? No, shirt. Okay. What else do I wear? What else do they have? Oh, jacket. They have jacket. Oh, pants. This is belt. Belt. Okay. Now, let's say, so let's think about the dependencies. You have to put your socks on before your shoes. Let me just make sure they have the arrows going in this direction. You have to put your shirt on before your jacket. You also have to put your shirt on, and you have to put your jacket on. I don't know this kind of thing because I don't wear a jacket or a tie, but they say that you have to put your jacket on before you put your tie on. You also have to put your tie on, your shirt on before you put your tie on, but this is implied because of transitivity. So vest comes before shirt. Do they say anything? For some reason, they think you have to put your belt on before your jacket. Not sure why. So your underwear has to go before your pants. Your pants have to go before your belt. I personally find it. They think your shirt has to go on before your belt. I am not sure. Socks, so your shoes. Yeah, okay. So underwear has to go on before your shoes. Your pants have to go on before your shoes. Okay, maybe I should just. Okay, So underwear has to go on before pants. Underwear has to go on. Pants has to go on before shoes. Okay, fine. Watch, socks and shoes. Yeah. No, wait. Tie has to go on before jacket. Okay. You can tell I don't know. Okay. Hat. So it's a bit different. I'm not violating copyright. Okay, so this algorithm is to do a topological sort. So a topological sort is you're seeing if there are any cycles. If there's a cycle, it's a catch-22. You have to put your X on before your Y, but you have to put your Y on before your Z, and you have to put your Z on before your X. So a few years ago, I was teaching this in Chile. My example was if you're trying to get a residency permit in Chile, you have to have an address, but before you can get an address, you need this. Before you can get this, you have to have a residency permit. Yeah, so the idea, so if there's a cycle, this algorithm is going to find it and return and say that you cannot topologically sort this graph. Otherwise, it's going to find a way of laying out these vertices such that all the dependencies go to the right. Okay. So that way you're going to say, okay, then the first thing I'm going to put on is this, then the next thing. Now, there can be several topological sorts because, for example, it doesn't matter when you put your watch on. It doesn't matter if you put your socks on before your shirt or your shirt on before your socks. Okay. So there are lots of different topological order. It just has to return one topological order. So the algorithm, which, yeah, I was actually going to look up, but then I thought it's probably too hard to find, and it's probably a sort of a bit too linear. But yeah, prerequisite courses, you could do that. Be like, okay, you have to have this before you have that, you have to have this. It's also, I'd also have to have faith that Tao hasn't created a cycle. So I don't think they have, but you never know. Okay, so let's start somewhere. Okay, so you pick a vertex. Now, initially, you don't, is this used for networks? I'm not sure. I could probably come up with a way you could use it for networks, but I don't know if it actually is. Probably. I mean, topological sort, it's databases, dependencies, dependency graphs in code. Right? You have like this module depends on this module. Basically, if you're figuring out sort of procedures where something depends on something else, then you have this. Okay, so what do we want to start? So pick some vertex. Don't pick like a vertex. So let's pick shirt. Okay. Now shirt is not going to be project manager. Yeah. So shirt is probably not going to be the first thing we need because if you look, you have to put your vest on before your shirt. I don't think you have a vest. Yeah. Oh, I mean vest like an under shirt. I don't mean like a suit, the vest. In which case you have to put that on after your shirt. Okay, this is undershirt. First time I taught this, I actually managed to mess it up and convince my students I didn't know how to dress myself. So then the next week I actually wore a suit and tie and everything. Okay, so let's say we start with shirt. So, oh, that's not very good. What happened to my red marker? Okay. So the start time of shirt is 1. Okay. So is that visible? Maybe we can do it in black. There. Okay. So the start time of shirt is 1. Now we go from shirt and we look around from shirt and we say, where can we go? We can go to jacket. So I think they call it discovery. So jacket, the start time of jacket is 2. And then you say, okay, well, can I go anywhere from jacket? No, so the time for a jacket is 3. You come back, you can't go anywhere else from shirt, so it's 4. So what do you know now? Well, you know that shirt has to come before jacket. So what you're going to do is, as you, let me think. I think you put these in order when you finished. I think it's finished. When you close the vertex, as you finish, you add it to the list. Yeah. Okay. After move. So now we're going to pick another one. Let's say we're going to pick hat. Okay, so this is 5, and closing finish time is 6. So we say, okay, well, that didn't really get us anywhere, but we finished it, we put it back in the list. All right, it has to be, yes, of course, it has to be. Okay, so let's see what else we could do. Let's do pants. So we go to pants, 7. So pants, we can go to belt. So this is 8. And now from belt, we can go to jacket. We've already been to jacket, so we don't want to go back. So we can't go anywhere else. So its finish time is 9. So we go to belt. It goes to jacket. And then we come back, and from pants, we say, oh, is there anywhere else we can go? Oh, we can go to shoes. So shoes, the discovery time is 10. Can we go anywhere? No. Finish time is 11. We go back to pants. We can't go, and we add shoes here. And we don't add any arrows. And we go back to pants, and finish time is 12. So pants, it says pants goes to shoes, pants go to belt, pants don't go anywhere else. Okay. So now we're going to move up and go to that. Okay, so does somebody else want to pick another item of clothing that we haven't visited yet? What's something exciting? There isn't really anything exciting. Okay, underwear, 13, but we can go to pants, but we've been there. We can go to shoes, but we've been there. So closing time is 14. Underwear goes to pants, underwear goes to shoes. And where else? We can go to socks. 15, we can go to shoes, but we've been there. Can't go anywhere else. 16, so socks. This I said to it always moves to the right. I haven't got enough words. I should have done it along the bottom. And finally, tie, usually not finally. 17, we can't go anywhere. 18, we can't go anywhere we haven't been. So oops. Okay, so this is what happens when you don't copy the example in the book. I should have put an arrow between shirt and tie. Okay. Oopsie. So let's pretend we did it. If I had done that, then then here when we went to shirt, we would have went shirt, jacket, shirt, tie. And so it would have been shirt, jacket, tie, shirt. But rather than correct all of the numbers, we're just going to forget about wearing a tie today. So, okay, what's left? Watch 16, 17, 18. Okay, 17, 18. Okay, so watch. Oh, and hat is already in. Okay, so the order is watch. So you put your watch on first. Okay, I guess you could. Then you put your socks on, then you put your underwear on, then you put your pants on. This seems to work. Then you put your shoes on, then you put your belt on. Like, okay, fine, it's working so. Then you put your hat on, then you put your shirt. I couldn't put my shirt on because my shirts are always t-shirts. I realized this can be problematic. A few weeks ago, I fell and sprained my elbow and couldn't lift my arm. And I had to really dig through my stuff to find a shirt that isn't a t-shirt. But I do have some. So this is actually consistent with my wardrobe. Okay, so if you have a button-up shirt, you can put your hat on first, then you put your shirt on, then you put the jacket on. Okay, so it works as long as we forget the tie because we didn't put the arrow on. I could have just copied the graph, but okay, so why does it work? It works in this example. Why does it work in general? This should be ending soon. Why does it work in general? Well, first of all, if there is a cycle, this algorithm is going to find the cycle, right? Because if you have a cycle, so right, you're marking, as somebody said, you're looking at vertices you visited. And if you ever start wandering around and you find an arrow pointing to a vertex that you've started, that's had a start time but doesn't have a finish time yet, then you have a cycle. Because, if you have a cycle and you pick, at some point you're going to choose or arrive at a vertex in the cycle, it's going to get a start time. S1, and then you're going to say, okay, this is going to get a start time S2, S3, S4, S5, and then you're going to get back here and it started, but it's not finished yet. If it started and finished, that's okay, because it means you chose it, you arrived at it earlier and you're done. So it's not an ancestor, right? So a cycle is sort of, if you're imagining the tree, it's not you're not getting a link back to somebody, to one of your ancestors in the tree, because it's finished already. So this is when, for example, we were looking at jacket. When we got to belt, we looked at jacket, it was already done. Okay, so it's not an ancestor. The problem is when it has a start time but doesn't have a finish time yet, that means you visit it and you've got to loop. So if there is a cycle, you're going to detect it. and the algorithm is going to say, no, it doesn't. Okay, so now suppose that there are no cycles. So you're going to start, when you order these things by finish time, you start with some vertex, and then you're going to explore, and your DFS. Your DFS from that vertex is going to include everything that's reachable from the vertex that hasn't been visited. Okay, so if it's reachable and it's already been visited, great. Then it's been dealt with, it has a finish time, and it's in the list, so it's further to the left than the place where you started. Otherwise, it will, in your DFS, when you visit a vertex, you will explore everything that can be reached, and then you will finish that stuff before you finish this vertex. So when you get back to the vertex for the last time and you finish it and you put it in the list, everything that can be reached from there is already in the list, right? Because if it weren't already in the list, then the DFS has missed it and you've implemented your DFS incorrectly. So that's topological store. So if you want, the proof is in CLRS. There's this long lemma this, proof that this works. But the main idea is, if there's a cycle, it will detect it. If there's no cycle, when you add something to the list, everything that's reachable from it has to already be in the list. Okay? That's okay. Because now we're on to our second third of the class. And so we're going to do, now this time I'm actually yes. I'm actually going to copy the graph. So if we had an in-person class, I might be tempted to actually wear a tie, but probably not. I think I have a tie. I think I may even have two ties. I haven't seen them for a while. They're probably in the top drawer. Okay, so now we're going to do another application of topological, which is strongly connected components. So strongly connected in a directed graph. So if you have a vertex and a vertex, vertex, and a vertex, and a vertex, and you can go, and this is U, and this is V. Okay, so you can go from U to V, and you can go from V to U. So they're in the same strongly connected component. A strongly connected component of the graph is a subset of the vertices, so a maximal subset of the vertices, such that for any vertices U and V in that subset, you can get from U to V and you can get from V to U. Okay, so it's maximal. It means this isn't going to work if you add any more vertices. Is it clear what a strongly connected component is? Okay, so within a strongly connected component, you can get from any point to any other point, and you can't add. No, it's maximal in the sense that if you add anything else, the property breaks. So if it were minimal, it would mean it's as small as it can be. But this is okay. I've used up time. Okay, so what's the algorithm is a little bit weird. Um, maybe there's a lighter version. I should get this on my e-reader. Okay. 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 This is about right. A, B, C, D. E, okay. So how do you find the connected components? Well, again, when you start, you don't know anything about the graph. So you're going to pick some vertex and explore. So which vertex do we want to choose? So we're going to do a DFS. Do people want to start at A again? Do we like starting at A? Okay. So opening time is 1. And then where can we go? We can go to B. Opening time is start time, opening time. And we can go to, well, we can either go to F or C, it doesn't matter. Let's go to F. Opening time is 3. We can only go, oh no, we can also go to E. Okay, but we will do that later. We can go to G, or from G, we can go back to F, but that doesn't matter. We've been there. We can go to H, so this is 5. And now we can't go anywhere from H except H stops. So it's 6. We go back to G, 7. We go back to F, it's 8. And now where can we go? Well, we go back to B, but we don't close B because it's we're not done. We go here, say, and it's 9. We can't go anywhere except F. We've been there, so this is 10. We go back. This is 11. This is 12. No, sorry, 11. And oh, if you start at A, you actually do everything in one DFS. Maybe that's why they don't start at A. Okay, 12, 13, 14, 15, 16. Okay, so that's our DFS. And what does it tell us? Not much. It tells us that the underlying underlying graph is, it tells us that you can get from A to everywhere. That's something. But we don't know if you can get from everywhere to A. So what are we going to do? We're going to compute what's called the transpose of the graph. Why is it called the transpose? So this just means you take every edge and reverse it. Why is it called the transpose of the graph? Because if you write the adjacency matrix of the graph, then the transpose of the graph, the adjacency matrix, the transpose of the graph is the transpose of the adjacency matrix of the graph, right? Because if before you had an arrow from A to B, so from the first row and the second column, you had a 1. Then when you take the transpose, that 1 is going to move into the second row on the first column. Okay, so it says that then it's going to say that there's an arrow from B to A. So that's why it's called the transpose. Okay, this goes here, this goes here. These actually, this first. This comes down. This goes up. Like this. This goes up. This self loop reverses, whatever. Okay, so everything is reversed. Okay, so now we're going to do more DF. The self loop stays the self loop. Yeah, I turned it around. That doesn't matter. So now we're going to do more DFSs, but I just have to remember the. Yeah. So we're going to do the DFSs in order of decreasing finish time. Okay, so you're going to start, this means that you're going to pick the vertex with the largest finish time, and you're going to start a DFS there. And then once you're in that DFS, you're going to ignore the finish time. Okay, so what's the largest finish time? It's A. And we say, okay, 1. And we can't go anywhere, so it's 1. Okay, so that tells us that this is a strongly connected component. No, sorry, because we can't get away. Sorry, that doesn't. Yeah, I didn't notice that. We did not do the closing time. We go 1, and we can get out of A. We go to E. So that's 2. And where can we go? We can go to B. So that's 3. And now from B, we can't go anywhere except A, and we've been there. So this is closing time 4, 5, 6. So this DFS explored these 3 vertices. That is a strongly connected component. Okay, now that we actually do this correctly. Okay, so that was 16, 15, 10. What's next? Well, it's 14. So we start here and we say 5, 6. So the start time here is 7. And where can we go from here? Well, the only place we can go is B. So that's 8. And then we are stuck because we can only go back. So we finish with B, 9. We come back. Now from C, we could have gone to B, but we can't because we visited there. So this is 10. And we can't do anything else. So this is a strongly connected component. And where else do we want to go? And 14, 13, 16, 15, 14, 13, 12, 11. Right. Okay. Next one is F. So we've done. So this is 11. And where can we go? We can go to G. So this is 12. And from G, we can go to C, but we can't. We've been there before. We can't get to H. So this is 13, 14. And that DFS is done. So that's a strongly connected component. And then H, 15, 16 is its only strongly connected component. And now we look at the book. Yes, that looks about right. Okay, so this is the algorithm. Do a DFS, and then transpose a graph, so just reverse all of the edges, and then do DFSs, and always, when deciding where to start your DFSs on the transpose, take the vertex that hasn't been visited, that has the largest finish time in the first DFS. Why does this work? Okay, so there are pages of proof of correctness in the book, but we don't really have that much time. I should put this on 2 minutes. We have 10 minutes. So I'm not going to go through all of that detail. Instead, I'm going to argue that if you think about the connected components, right? So imagine you knew the connected components somehow, and you drew another graph where each connected component was a single vertex, right? So you have a vertex, and this vertex this represents the A, B, and C. Okay, so A goes to B, B goes to C, C goes to A. But we don't care what's in there. This is just going to be an argument about how this works. Okay, now in the original graph, okay, and you have C and D. In the original graph, you can go from you can go from B to C. So this means you can go from this vertex to this vertex. You can get from this strongly connected component to this strongly connected component in the original graph. Forget the transpose. Why is it important to detect strongly connected components? So you don't get stuck when you go off wandering. I hadn't actually been anticipating this question. Because it's useful to know that like A can send to B and B can send to A. So why is it important? In networks, sort of important, communication networks. What do I use it for? I have used it. I'll have to get back to you on that. But for example, if you go out for a drive or something like that, and you have a map of the city and it shows one-way streets, or if you're designing your city with one-way streets, you want to be sure that it's all one strongly connected component. You don't want there to be places where somebody can drive down a street and never get back. I'm not sure, there probably are places like that. I mean, maybe you can get back eventually, but maybe not. Okay, but you can see that would be bad. What's enough? Okay, I will think in the lecture notes. I will try to think of I'll try to find applications. But graph theorists love this stuff. So you get certain properties like tokens. You don't want to get stuck if you're token passing. So you don't want the token to get stuck somewhere. Or maybe you do. If you're analyzing certain finishing times, then you don't. Okay, but for now, proof of correctness in 6 minutes. Okay, so you can go from here to here. Now, where else can you? Okay, so you have F and G. You can get to F and G. So you have F and G. you can get from A, B, and C to F and G. You can get from C and D to F and G. Okay. But notice that you can't get from F and G back, right? Because you can't, if you go from A, B, and C, if you could get to F and G and then somehow you could get back to A, B, and C, then it would all be one strongly connected component. Yes, there should be. I mean, if okay, check it. Something like, I don't really think that. Not real dynamics, abstract dynamics. Okay, so what else is there? Then there's just H, and you can get from F and G to H, and you can get from C and D to H, but you can't get from H to any of these. Otherwise, it would be in the same strongly connected component. So what is this graph? This graph is a DAG, a directed acyclic graph. It's not a tree. It would be nice if it were a tree. But it's, in general, it's a DAG. Now, when we're doing the DFSs here, we're starting with a vertex, and we're doing it in decreasing order of finished, right? So if you think about it, is it possible for somebody in C and D to have a smaller finish time than H? No, it's not. Because if in the DFS, no, we have one DFS. You do, I think, an example. If you started your DFS at C and D, you'd actually get all of the stuff reachable from C and D. So you get all of these. So now, if you consider, so if the thing that you can reach the most from, this is going to have the largest finish time. Somebody in here is going to have the largest finish time, because if you start in here, your DFS is going to take in everybody else, everything that's reachable from this component. So forget these little graphs in here. I actually need these. Forget these for a moment. Those don't matter. So you're going to be starting with somebody that can reach a lot of stuff. You can't, when you're doing your DFSs in the transpose, you can't be starting at one of these where this, you could go from here to here, and you start your DFS in the transpose here when this hasn't already been done. This stuff in here is going to have a larger finish time than stuff in here. Why does that matter? Because when you take the transpose, you're essentially reversing all of the edges here. Okay. So now this is going to look like, because if you could get from F and G to H, when you flip the edges around, you can get from H to F and G. Okay. So before you could reach everybody here, so this from this vertex, from this. So now somebody in here is going to have the largest finish time. So we're going to start with somebody in here. Now, everybody in here could reach everybody else in here. And that property remains true when you reverse all the edges. Okay, you don't change the connectivity within a strongly connected component when you reverse the edges, when you take the transpose. So now you're going to start in this vertex, you're going to explore it, and you're going to see everything in here, and you're going to be stuck. You can't go anywhere from here because you've reversed the edges. You could leave before, but now you can't. So now it's sort of so you're going to, if there's somebody that can reach a lot of stuff, it's going to have to have a larger finish time than them. So it will be considered first, and you won't, if there were an edge that originally led here and now leads out of here, then you would have considered the connected stuff in the connected component here first. So you still wouldn't be able to leave. So this we're going to deal with first. Now next, before you could go from C and D to F and G. So that meant that if F and G, if you had the C and the stuff in this connected component has to have a larger finish time than here, right? Why? Because if you started DFS here, then you can't get here. And that means you do this part afterwards and the finish time here are big. So if you started DFS here first, then it'll finish and you'll do a DFS here next and the finish times are larger. Suppose you started DFS here first, then you'll reach here and deal with this connected component and come back, and the finish times for somebody in here will still be large. So that means if you could originally go from C and D to F and G, somebody in here will have a larger finish time. So we're going to take this. Now, because these had a larger finish time, we can't go from here to here. So we're going to finish with this one. You're stuck in this connected component. Okay. And then so the property is, if originally you have a connected component and you have sort of edges leading in and out, then the stuff the connected components that are leading in, somebody in this connected component, if this is a connected component, this is a connected component, these are connected components. If it looks like this originally, then if you could get from here to here, somebody in here has to have a larger finish time than anybody in here. So that means that when you take the transpose and reverse all the edges, you're going to deal with this connected component first, so you can't go back to it. So you can't get out. And now all of these things that were out edges are now in edges. So when you started DFS in this connected component, you can't get out. So it will explore the whole connected component, because from everything from anywhere in the connected component, you can reach anywhere else. That holds true when you reverse the edges. So you're going to see everybody here and nobody else, because you can't go back to a previous connected component. So this algorithm works. And it will be explained in the lecture notes, and we have to get on to this algorithm. Questions? Okay, and I should remember to find some applications. There are applications. They're in the book, but I didn't read the applications. I just read the proof. Okay, I think this proof is easier than the proof in the book. I would take the whole lecture. Okay. So that's topological sort. I'm sorry, that's applications of depth first search. Now we're going to consider sort of an application of breadth first search, which is Dijkstra's algorithm, which is finding a single source shortest path with, so this is single source shortest path with non-negative edge weights. And I think this runs in O of V plus E time. Yeah. Okay, so this is usually n and this is usually m. So it's the number of vertices plus the number of edges, I think. Okay, so in the next classes, we're going to see all pairs shortest paths. So this is sort of finding the shortest path between any pair of vertices, and also how to deal with negative edge weights. So in the proof of correctness, which I hope we'll have time for today, we're going to see why Dijkstra's breaks down if they're negative, because we're going to need that assumption to prove it correct. You can deal with negative edge weights. Floyd Bush, I'll have to, I get these. Okay, and there are algorithms, even if you have non-negative edge weights, there are algorithms for finding all pairs shortest paths that are faster than running just Dijkstra's. Okay. So remember, you implement a depth first search with a stack. You implement a breadth first search with a queue. Dijkstra's is sort of a breadth first search, but you use a priority queue. Okay, so what are people in previous years? People mix up finding a single source shortest paths algorithm, the problem of finding single source shortest paths, with the problem of finding a minimum spanning tree. Remember, we said in when we were designing the minimum spanning tree, the example is, ooh, you're a county planner, and you're trying to figure out how to pave the roads to connect everything up, and you want to spend the least amount of money because you're a good county planner. Now imagine that you're a corrupt county planner, and you live in one of the towns, and you just want to pave the roads such that you can get wherever you want to go as fast as possible. And you don't care how much money you spend. You just want to get from you want to get from where you live to wherever, and you don't care about other people. Right now, this is going to be a tree because you're still not going to have a cycle, because if the shortest path, if you live at A and the shortest path to B is like this, and the shortest path, it's if you had a cycle, live at A, and then there's a cycle, right? Then so this is B, and this is C, and this is D. Well, if you've got a cycle, it means that that you've got two ways of getting to C. Well, one of these, either they're tied, in which case you can forget one of them, or one of them is well, why would you have this edge to C as the cheapest way to go from A is going? So it's still a tree in general. Like, you can assume it's a tree. So it's still going to connect the graph. It's still going to be a spanning tree, but the cost to the taxpayers is not guaranteed minimum. All you care about in this problem is you want to be able to get from A to any other point as quickly as possible. So that's 17 minutes. Okay, so what are you going to do? I'm going to keep on. I'm just going to take oops. This is this the example for dextrose? I'm just going to take it anyway. I need an example graph. And I need it quickly. Canvas. Okay, so this is SUB XY. Okay, so normally you do a BFS with a Q. You do Dijkstra's with a priority Q. So what do? So S is where you live, you, the corrupt county planner. And these are the distances of the roads, the time it takes to cross the road. And now, so this is, okay, so now, oh, actually, maybe this is not going to, yeah, in the case of an undirected graph, you get a tree and everything is connected. In the case of a directed graph, you can get from S to anywhere else, but this is the case of like maybe you can't get home. So so maybe you're gonna, so you only care about, in this case, you only care about getting there, and then you're gonna be stuck there. Then you. So in this case, it's directed, so it's not guaranteed to connect. There's going to be an edge, but it may not be going the right way. So it's okay. We could just take the arrowheads off and make it undirected. Okay, whatever. So, or is that? Yeah, no, it is undirected. Okay, so what you're going to do? You're going to start. I really want. Okay, so this should work well. So we can get from S to S in time 0. Yes, that's the book is expensive. That's why it's not mandatory. I forget how much I paid for it. Like I bought mine in the 90s. So it's probably cheaper back then, but it was fairly expensive in the 90s. There are copies in the library. But yes, it's for people who are going to keep taking algorithms, it's a good investment. I mean, especially if you're going to end up teaching algorithms. But otherwise, it's got way more material than, right? Because this is over 1,000 pages. And longer, whereas the course notes are probably going to end up being like 200 pages. And a lot of that is just me rambling and not being really on topic. So if you really want to know, get the book. But if you're not planning to take this any more algorithms courses, if you have a lot of money, then go for it. But okay, Dijkstra's algorithm. So you can get from S to S in time 0. So what you're going to do at any point, you want the invariant that you have some vertices you can already you already know the distances to, and for all the vertices. For all the vertices that are one step away from what you know the distances to, you have sort of candidate distances, right? Which is, for each of these, they're labeled with the so if you can get to this is a distance d1, and this is distance d2, and this is c1, and this is c2, then this will be labeled with min of d1 plus c1, d2 plus c2. Okay. So it means that everything that's one step away from where you've currently got the distances to, you've sort of figured out how much it will cost you to get there in one more step. From the stuff that you already know the distances to, how much does it cost you to get there in one step? What's the minimum? And the minimum, and you're still considering the distance from S. So this cost is this d1. And this cost is d2. So the cost of getting here is the minimum of getting to this and taking this step, or getting to this and taking this step. Okay. So let's see how it works. So you say S. So this is going to have cost 3, and this is going to have cost 5. Now, maybe 3, maybe 5. Okay. Now, of everything, once we've got these labeled, of everything we can get to in one step, we're going to choose the cheapest thing, and we're going to go there. And we're going to say, okay, is this 3? Yes, this is 3. So this is a 0. We really know that we can get from S to itself with cost 0 and not less, because there are no negative weight edges. In particular, no negative weight cycles. Okay, now from here, we look and we say, where can we, then this we can get from S. When we confirm that this distance is 3, then we look and we say, maybe we can get to this with cost 9, and this is still cost 5. Okay, so now the sort of the cheapest tentative cost is 5. So we're going to say, we're going to add this, and we're going to say, yes, this is really 5. And now, this is kind of boring. Oh, this edge goes the other way. And lots of stuff is working out to be the same. Why did they do this example like that? Okay, so you say 3. Let's make this edge 3. Okay, we'll change this example. So we're going to make this 3 so that it's better example. This is dangerous, and we're going to make this, yes, we're going to make that. That's going to make things more interesting. Okay, so we were saying this is 3, and this we could get here with cost 9, But now we can also get here with cost 8, right? So it says, was it 9? Well, it was 9, but now maybe it's 8. And here, we can get here with cost 11. So now that's everybody. So we have we've confirmed that these are the distances. These distances are confirmed. These are tentative. Now, of all the tentative distances, the stuff at one step away from the stuff we've confirmed, the cheapest distance is 8. So we say, okay, 8 is no longer tentative, it's confirmed. And now from 8, we look and we say, okay, where can we go from 8? We can go with cost 2 to here, so that makes this a 10. Okay, so the idea is you do this with a priority queue. And that means when you confirm a vertex, so priority queue is going to contain all your tentative stuff. You're going to take the thing that has minimum tentative cost, and then all of its neighbors, you're going to look at the so when you add somebody to when you confirm somebody's cost, you're going to look at its neighbors, which some of them may have infinite cost because there was no way to get there before. And some of them may have, so say this has cost 5, and this is 6, and this is a tentative cost of 10. Then you say, well, I can get there with cost 11, but I could already find a cheaper way there. Also this, if this has cost 2, then now you say, okay, it has a tentative cost 7. So you cross out the infinite. And maybe here, this is cost 3, and it was tentative cost 9. Now it's tentative cost 8. So what you're doing is, for all of the vertices, you're checking, and these tentative costs are their priorities, the priorities with which they're in the priority queue. If you can decrease the tentative cost, then you change the priority. If it was infinite, it wasn't in the queue before. So now you assign it a priority and you put it in the queue. Okay. So you see how to implement this with a priority queue, and I probably have like almost no time to teach proof of correctness. I have 4 minutes. Okay, but that should be enough. Because this is basically a greedy algorithm. Okay, how do we teach a greedy algorithm? Before we take any steps, we haven't made a mistake. So actually, when we label this with 0, okay, yeah, when we label this with 0, let's assume. Okay, before we label anything, before we confirm the distance to anything, we haven't mislabeled anything. We haven't assigned any. Notice that when we assign a distance, we actually can get there with that distance. The problem is really going to be, what if we assign something a distance and there's a cheaper way to get there? So, because yeah, in the book, this was a 4, and so everything worked out. It was boring. Okay. Why is this? So before we do anything, we're fine. So let's just assume there's no negative weight cycle from S to S. So then we're okay. What do we do? S, and we say we can get the minimum distance from S to S is 0. Because if there's something like a cycle with total cost -1 that goes from S to S, then actually it's undefined, because you can just keep going around the cycle and distance gets, the cost gets less and less. So that's a nasty case. You can't deal with negative weight edges. You just don't want to deal with negative weight cycles. Okay. Well, you can still work out the costs for the stuff that's not in a negative, that doesn't have a negative weight cycle on the weight. Okay. Next class. Let's assume, so this is the stuff we've confirmed. So before we take any steps, or even when we label this with 0, let's assume that's okay, because there are no negative weight cycles. Okay. Let's suppose that up to step I, we haven't made any mistakes. So this means that we've labeled with distances a number of vertices. I could be using this picture. I could use this. Yeah, I'm going to redraw that. Okay, so now let's consider that this is the cheapest vertex that we can reach. So this is S, and we have some confirmed cost here, which is D1, say, distance 1. And the cost of this edge is C1. And we say, okay, of all of the things we can reach from one step, from this piece that where we've confirmed the costs, this is the cheapest. And so our algorithm labels it with D1 plus C. So here I'm saying like the minimum of all of the ways to reach this in one step is D1 plus C1. We label it with that. Okay, so why is that not a mistake? This is a little bit different than degree. It's a little bit different than degree 4, but it's basically the same. Perhaps there is a difference between our solution and the opposite. If there are 2 edges from one node with the same weight. Yes. So it could be that D2 plus C2 is equal to D1 plus C1. But the thing is, I actually still have a few minutes. I have 3 minutes. That should be enough. We're not actually, when I said we're still getting a spanning tree, we actually don't need the tree, particularly. We just want the distances at the moment. Because if we get a tree, if the distances are correct and we have a tree that realizes those distances, it doesn't matter, like that's fine for our purposes. We get the cheapest, it doesn't matter if it's unique, okay? So I'm just going to claim that if we label it with this distance, we are okay, that later on it can't turn out that there is a way to get there that's cheaper than D1 plus C1. And okay, well, suppose there were a way to get there that's cheaper. Well, that way at some point would have to leave this set of correctly labeled vertices. And it would have to, so it would leave, and then there would be a path. So directed path. This shouldn't be a waving line, this should be. So it has to leave. Maybe this arrow goes directly here, or maybe there's some section of this path that is outside the stuff we've already labeled. But you see that there has, if there's a cheaper way to get there, if there's a cheaper path, it has to start at S and leave this and get there another way. But the thing is, that means the cost here is something like D2, and this is something like C2. So this is why it's a little bit different here. So the cost here is D2 plus C2. And by the way we've ordered these vertices, by the order in which we're considering these vertices, D2 plus C2 is greater than or equal to D1 plus C1. Because if it weren't, we would be labeling this before this, okay? But that means that as long as this path doesn't have a negative cost, going from S, going to this with cost D2, and then taking this, that's already used up the same as the cost of going from here to from S to here and from here to here. So the only way this is a mistake is if this path contains negative weight edges. And we assume there are no negative weight edges, so Dijkstra's algorithm is correct. If there are negative weight edges, Dijkstra's algorithm breaks. You can find cases in which it doesn't return the correct answer. And I am 1 minute over time, so we're going to assume everybody understood that. And if not, eventually when I get caught up with the lecture notes, there will be lecture notes. And the little camera stopped recording just now. So I will finish more or less on time now. See you on Wednesday when we do like all pairs and negative weights and stuff like that. Okay, is everything good? Cheers, you too. Ending recording. Ciao. Oh, no, that doesn't.